Now, section 5-5, theorems about roots of polynomial equations. We are definitely trimming this down quite a bit. There is a lot going on in 5-5, and we only need to do just a basic surface level understanding of section 5-5. So I want to definitely kind of cut through a little bit of the fluff that's there, because honestly, there's a lot of this stuff that is in 5-5 that you will see in your functions class if you do find yourself in a functions class later on here at Lakeview. But what I want to do is just simply go through some of the more essential stuff that's in 5-5, and then you can dig deeper into it once you find yourself in functions class. The first thing I'd like you to think about is think about the quadratic formula. The quadratic formula looks a little bit like this, doesn't it? X equals, and then we have the opposite of b plus minus the square root. We have b squared minus 4 times a times c, all divided by 2a, provided that we are solving this algebraic equation here, right? Ax squared plus bx plus c equals 0. Now, key symbol I want you to focus on is right here. With the quadratic formula, what is absolutely unavoidable is that plus minus sign right there, okay? So unless, of course, the trivial case is if you end up getting 0 inside that b squared minus 4ac, in every other case, you're going to have a number plus that square root and also a number minus that square root by solving with the quadratic formula, okay? So in other words, you can't have the positive radical without the negative radical. In the math biz, we have a name for that. We call that a conjugate, okay? So all this right here is saying is that if we have a polynomial that has with rational coefficients and we end up with some irrational solutions, when we're graphing it, and we end up with solutions that doesn't cross at the integers, at whole numbers, but at those in between, those decimals, then what this conjugate root theorem is saying is that you cannot have a plus b, the square root of b, as an answer without its buddy, a minus the square root of b. So if a plus the square root of b is a root, then a minus the square root of b is a root. The same is true if, for some reason, that number underneath the square root, that b squared minus 4ac, this guy right over here, what happens if that's a negative number there? Well, you still can't have one without the other. The only difference is that now you're going to get I in an imaginary unit here. So they're saying the same thing. If a plus bi is a root, then a minus bi must also be a root. So let's just practice that, okay? So here are 4 examples, and all we're trying to do is just write the conjugate of each root. So suppose we had one root of 1 plus 3i. If 1 plus 3i was a root, then what must also be a root is 1 minus 3i. Do you notice that I did not write this? Negative 1 minus 3i. So what we are not doing is I am not telling you guys to write the opposite of the root. Opposite of the root would be us taking the opposite of each one of those. See, I'm doing distributive property there. If it was the opposite, I'd be saying the opposite. I'm not going to use this word conjugate very loosely. I'm using that with a purpose because I'm intentionally telling you what a conjugate is. And what a conjugate is, it's only the opposite of either the radical, the irrational portion, or the imaginary portion. That's it, okay? So you leave that first part alone. Okay, these are the only ones that we're going to change to the opposite. So, conjugate of this one over here, 4 plus the square root of 7. Here we'd have negative 2 plus 9i. And then over here, keep it 15, but now be minus the square root of 10. Okay, so that's how conjugates work. And you can't have one without the other. Okay, so if we take a look over here at using that conjugate root theorem to identify roots, you will routinely get questions like this. Suppose we had a quartic polynomial. Doesn't that mean it needs to be to the 4th power? And I'm kind of curious about why. Well, I guess I understand why they're saying it here, because they want you to use the conjugate root theorem. And if they said that the square root of 2 is a root, and 1 plus I is another root, then what should the other 2 roots actually be? And so what they want you to do is they want you to apply this conjugate root theorem. That's it. Don't overthink it. So if I'm looking at this square root of 2, what they're trying to help you along with is think of that square root of 2 as looking like this, 0 plus the square root of 2. And you cannot have 0 plus the square root of 2 without its buddy, 0 minus the square root of 2. In other words, if the square root of 2 is a root, then a negative square root of 2 must also be a root. And do you see how they repeat this message with 1 plus I? If 1 plus I is a root, 1 minus I must also be a root. So when we look down here at this one, this is kind of an interesting problem. And going back up here anyway, I want to point out something here. A quartic polynomial, notice that we have two real roots, square root of 2 and negative square root of 2, and two imaginary roots. Okay? Something to keep in mind, foreshadow alert to 5-6, is that these conjugate roots always have to come in pairs. Okay? So I cannot have square root of 2 without its buddy negative square root of 2, cannot have 1 plus I without its buddy 1 minus the square root of I. Okay? They have to come in pairs. So when you look at this problem right here, it says cubic polynomial. So there's 3 fundamental theorem of algebra to tell us there would be 3 complex roots. Notice they give us 3 minus 2i as one root. Okay? Another root is 5 halves. What is the one additional root? What they want you to understand is if you look at that 5 divided by 2, there are no conjugate roots that are with 5 over 2. It's like if I were to ask you this, ladies and gentlemen. If I wanted to give you a complex number or a irrational root, like say this, 2 plus 0i, aka just 2, right? If I do a conjugate of that, wouldn't I still have just 2 minus 0i? In other words, it would still stay as 2. Okay? So when you end up with just real numbers, like the 5 divided by 2, we get to leave that alone. The only one that we actually take a conjugate pair with is anything that would have either an imaginary part or an irrational part. So if 3 minus 2i is a root, then 3 plus 2i must also be a root. So what is that one additional root? That one additional root? This guy right there. Nothing more, nothing less.